This is hydrology, USGS regression methods, Chapter 9, Lecture 1. I'm Dr. Marty Matlock. First, a comment about my COVID haircut. For future generations watching these videos, this is a bit of a social record of the times we are living in. Our barbershops have been closed for 4 months. So this is what it looks like when you put a number 2 guard on and go to town. I know I'm not alone out there. Let's get started. Water balance in the watershed. We know at this point that what we're trying to calculate is runoff from the watershed, effective runoff, based upon initial abstractions from precipitation. We also understand very clearly how to calculate those abstractions and how to get effective runoff. Our previous lectures described how we can actually quantify that runoff over time and build a hydrograph. We've worked on different types of hydrographs. Now we're going to talk about unit or dimensionless approaches to hydrographs. There are 2 dimensionless approaches, the USGS regression approach and the unit hydrograph method. The USGS regression approach really falls under a synthetic hydrograph model, but I put it into Chapter 9 because it's very much an extrapolation of knowledge from one watershed to another without actual explicit measurements. And so it's sort of in between a synthetic hydrograph and a unit hydrograph method because it uses, as you'll see, dimensionless strategies for characteristics of the watershed. The methods are clearly defined. These are well-established methods. We've been doing this for 50 years almost. The USGS has extensive documentation. You start with National Stream Flow Statistics Program. That's the NSS program. This program was just being developed when I was in graduate school, and it's now in full implementation. So you have the benefits of this. This is progress for hydrologists, and it's an incredibly valuable tool. You've seen a bit of it already with StreamStats, the integration of GIS with this process. These are the gears and axles behind StreamStats. So the USGS regression method document is available for review. We know that regression equations are commonly used for estimating stream flow statistics at ungauged sites. Regression equations are just y is some function of x. They're developed by statistically relating the computed stream flow statistics to the physical and climatic characteristics of the watershed for a group of gauging stations that have virtually natural stream flow conditions within a region so that you can extrapolate them to others. Regression equations enable the transfer of stream flow stats from gauging stations to ungauged sites. Remember, that's the condition 5 that we're almost always operating in, where we have no data, simply by determining the watershed and the climatic characteristics needed for ungauged sites and solving the regression equations based on these input values. That's our approach for NSS. USGS has been developing these things since the 1960s. I was born in 1962. I'm almost 60 years old. That's how well developed and extensive these are. Many people started their careers working on this process and have already retired. So this is a multi-generational hydrologic cathedral being built by our federal investment and resources for future generations. Support and justification for applicability of these equations are well documented. Regionalizations of stream flow data by state and territory is nearly complete. You can see the eras of completion started out in Michigan in the 70s, and then we've worked our way through the 90s. Basically, you can track federal investment in USGS based upon when these things were done. So Arkansas, the sort of heartland region, has just been recently completed. Puerto Rico was completed in the 90s. These data sets are always being updated. Once they're established, updating them is a relatively simple process. I say relatively simple, but it's a whole lot more simple than creating them from scratch. The regression method evolved from 6 techniques. The index flood procedure, that was what was used from the 40s to the 60s, where you had an index flood and you applied that to other locations. The ordinary least squared regression procedure, which was the first stage of regression, used in the 70s and 80s, and those were the early states, Michigan and others were used. The weighted and generalized least squared regression procedure, first used in the 80s and still used today. So we started with the weighted, then the generalized least squared. The region of influence procedure, first used in the 90s, and then StreamStats, an emerging automated procedure for estimating streamflow statistics, which we use today. We're not going to go through all 6, but it's important to think about and understand where the deep background here. The index flood procedure consisted of 2 major parts. Development of basic dimensionless frequency curves, that's the dimensionless part, representing the ratio of flood discharges at selected recurrence intervals to an index flood, that's the mean annual flood, and development of a relationship between watershed and climatic characteristics and the mean annual flood to enable the mean annual flood to be predicted at any point in the region. So this is when the value of this statistical approach became apparent to hydrologists around the nation. The combination of the mean annual flood with the basic frequency curve, expressed as a ratio of the mean annual flood, provided a frequency curve for any location. The determination of dimensionless frequency curves involved a graphical determination of the frequency curve for each station using the Weibull plotting position, determination of homogeneous regions using a homogeneity test on slopes and frequency curves. They had to be the same. Computation of the regional dimensionless frequency curve based on the median flood ratios for each recurrence interval for each station. The homogeneity test used the ratio of the 10-year flood to the mean annual flood to determine whether the differences in slopes of frequency curves for all stations in a given region are greater than those attributed to chance. This is good science. This is a lot of sweat. This is hard work. This hard work has occurred over 50 years. This is an incredibly valuable approach, and it's rare. The United States has one of the best hydrologic analysis systems in the world. Don't think you can use this in Malaysia or even in Munich, because you won't have the data. The 10-year flood discharge was first estimated from the regional dimensionless frequency curve. 95% confidence interval for the recurrence interval of this discharge, as determined from the individual station frequency curves, was determined as a function of record length. If the recurrence interval for a given station was within 95% confidence bands, then it was considered part of the homogeneous region. Otherwise, it was in another region. The mean annual flood, as used in the index flood procedure, was determined from the graphical frequency curve to have a recurrence of 2.33 years. Remember when we calculated the probability of actual recurrence of events is longer than the t of those events? So the mean annual flood, it has an actual recurrence of about 2.33 years. Rule equations in this approach are based on watershed and climatic characteristics that can be obtained from topo maps, aerial photos, rainfall reports and atlases, or digital map data derived from other sources. So that's the way we extrapolate to areas without data. Drainage area or contributing drainage areas appear in nearly all the statewide rural regression equations given in NSS. The other most frequently used watershed and climatic characteristics are main channel slope and mean annual precipitation. So now we have the variables that are used in the regression equation. Again, relax. You don't have to do this. You don't have to learn 50 years of process in 3 hours. What we have to do, though, is understand the philosophical and technical background for the tools we're using. The regression equations are generally reported in the following form. The rule estimate of streamflow statistics, rule Q, equals AX to the B, Y to the C, Z to the D, where X, Y, and Z are watershed or climatic characteristics used as independent variables. Remember, Y equals MX plus B is a straight line. And A, B, C, and D are regression coefficients developed by the homogeneous watersheds. So this is a line-fitting method. And this, as you can see, because of the exponentials, is not a straight line. So what we're doing is we're fitting a quadratic equation here. It's not really, because there's no, it's just three variables, it's just x times y times z, but they're exponential relationships. But so we're curve fitting a line. So the National Stream Flow Statistics method can estimate stream flow statistics for basins that span more than one hydrologic region within the same state on the basis of percentages of drainage area in each region. We typically keep them to state levels, but if the two different estimates are assumed to be independent, weighted flood frequency estimates computed like, as you see, we do log transformation of the weighted estimate flood peak discharge Q, because Q is what we're always after for recurrence interval T, a 5-year flood, a 2-year flood, a 50-year flood, a 100-year flood, at the gauging station for a watershed, GW, equals the number of years logged at that gauging station times the estimate of QT for that gauging station and the regression. Let's see, QTGS is the estimate of QT derived from systemic flood peaks, plus EQ, which is the equivalent years of record determined for the regression equation, times QTGR, which is the regression equation estimate of QT, over N plus EQ. So it's a ratio. Now, again, you don't have to do this, but you need to understand that these regression methods are robust. They're based upon causal relationships. They're based upon statistical analysis of causal relationships. And so they have significant competency. To obtain a weighted peak flow estimate of QT for occurrence interval T at the ungauged site, which is QTUW, the NSS program must first be used to create a scenario of weighted flow estimates for an upstream or downstream gauging station. The weighted gauging station estimates, QT for the gauge weighted, is then used to obtain an estimate for ungauged site based upon flow per unit area at the gauging station by use of the following relationship. Now, this is not a complicated relationship, has a lot of variables. Absolute value of the difference between the drainage area of the stream flow gauging station and an ungauging station is delta A, which is A of the gauging station minus A of the ungauging station. That's just area. That's easy enough. QTUR, which is the stream flow estimate for recurrence interval T, flow for a particular return storm at the ungauged site, derived from the applicable regional equation, which we just saw. So that's the way we move to this process. It's not that complicated. It's just a ratio of areas. The regression equation is in the NSS programs, are applicable and representative of the data used to derive them. Because users of this program are responsible for the assessment, your engineers, you can't say USGS made me do it. You have to understand the limitations of it. So the interpretation of the computed results have the following limitations. Now, I've provided 6 of these limitations, which I see as the most critical, but there are 10. You need to review all those limitations. If you're going to use this method, you've got to at least understand what it's doing. You don't have to be able to repeat it because, again, 50 years of effort. But you need to at least understand what it's doing and why. So estimates from the regression equation in the NSS reflect natural flow conditions. If this is highly channelized, you can't use it. The rural flood frequency equation and all equations for estimating other types of stream flow statistics can be used to obtain estimates of natural flow conditions on urbanized streams. So you can use it, but you have to be careful. The magnitude of the true standard errors of estimating of ungauged sites will be larger than reported average standard errors, so uncertainty goes up. Drainage area must always be determined because that's a required value, and that's why in StreamStats, that's the first thing you do is get your drainage area. Flood frequency curves for watersheds contained in more than one region cannot be computed if the regions involved do not have a corresponding T-year equations. Now, fortunately, almost all the regions we work in have those. In some instances, the maximum flood envelope value might be less than some T-year computed peak discharges for a given watershed. It may underestimate them a little bit. And that has to do with just simply the allocation of flow based upon watershed area. So see the document for full limitations. The USGS developed regression calculations for every state. Arkansas is relatively recent, 2013. Take a look at this document. It's available for you at this link. It's also available on the class site. It's nice. You can see here's a USGS station under flood conditions with water coming under through this looks like a double channel conveyance, and even a standing wave at the end exit as this water converges. And here's another at a bridge that looks like it's at flood stage as well. It's out of bank, so above bank full. So take a look at this document, be familiar with it. It's part of your professional responsibility to understand these processes. Arkansas is a complex state. I think most states are. Arkansas has many different zones. These physiographic sections also pretty closely aligned with ecoregions, and now they kind of align with major basins because they're using similar processes. But we have the Mississippi Delta region here. So West Gulf coastal plains. You might not think of Southeast Arkansas as West Gulf coastal plains, but they are. We have the Arkansas Valley, which you're familiar with, the Ouachita Mountains, the Boston Mountains, which are the mountains to the south of Fayetteville, and then the Ozark Plateau. That's called the Springfield-Salem Plateau, according to geologists, but the rest of us call it the Ozark Plateau. So, and then the East Gulf coastal plain over in Mississippi and Tennessee, Louisiana. Up in Oklahoma, Osage Plains. So this is sort of the breakdown of the regions. And these regions are important because they determine how you cluster and analyze sites based upon similarities. So look at the representation we have where we have continuous recording sites, the black triangles, and the open triangles where we have crest stage gauging sites. So they can at least measure the point at which, and these are usually static sites where you have to go out and read them after the storm. Usually it's a floating ball with some sort of an indicator or in a channel which shows you what the total height, maximum height was during some event. And those are read after the events. They're not continuous. So we have a pretty good network across Arkansas of gauging stations. And those gauging stations were used for developing the regression method in Arkansas. The drainage area ratio, as we've talked about, drainage area is the most important variable for the regression method. Drainage area is the most important variable, assuming you're in at first it has to be a homogeneous drainage area, but once you're in a homogeneous area, then the area is the most important variable, was used to determine if two nested basins are of sufficiently similar size to conclude they are essentially the same basin for the purposes of a regional hydrologic model. Can you take the flow from one and apply it to another? If the drainage area ratio is large enough, even if the pair of streams gauges is nested, they will reflect different hydrologic responses because storms of different sizes and durations affect them differently. We know that. So if we take the maximum, what we do is to find the drainage area ratio, we take the maximum ratio of DRN area I over DRN area J, or DRN area J over DRN area I. We just take the maximum of those two, where I is the GIS-derived drainage area at the site, and J is the GIS drainage of site I, and J is GIS-derived drainage area of site J. So let's say that you have site J happens to be the one that has the gauging station on it, and so you wanted to see if site I will work. You take the drainage area ratio, figure out which of these two is the largest, and you put it on the top. And that's the way you figure out what the DIR is, the max. So that's the ratio. StreamStat does all this for us. You've used this already in class. StreamStat is a streamflow statistics and spatial analysis tool. It has a lot more tools in it than just StreamStats, but we're focusing on that. The web page is available. It's an amazing resource. It's a web-based application. StreamStat works with the web browser on personal computers and mobile devices. So you've already used this. Get to know this site. It's a major asset for you. So review the user's manual. The user's manual is available. The user's manual is basically how to click and poke and prod around the program. The statistics are defined. That is all the names of all the things it reports. You don't know what APR D15 is. Well, it's the April exceedance flow 15% of the time. And this is the way you find it. They've got a whole, this thing scrolls for, I bet, 350 labels. So go through these labels. Each of them have a number, and this is the way you code things. But we have their English units and their metric units, so you understand what it is. Bookmark this link. Do the same for the basin characteristics, so you get to know what you're looking at when you look at the StreamStat reports. For our project site on Upper Town Branch, see, here's Town Branch. Many of you are asking, why is this, what's Town Branch? Well, this is what we've been working on since week 1. And this is the site just before Town Branch converges with the stream coming across MLK Walker Park. So this is our site, and we've delineated this already with StreamStat, and it gives us a significant amount of information. And look, we can create all sorts of nice quality basin maps here with StreamStat. We also notice that we have a gauging station here, a gauging station within our site. This is incredibly powerful because this means that within this basin, our data for extrapolating to this location goes up significantly because we have a gauging station here. We also know that we have a rainfall site from NOAA at Drake Field, which is very close to our site. So that means we have pretty good information about this site. And look at the information you can then select: low flow stats, seasonal flow stats, monthly flow stats, probability stats, general flow stats, peak flow stats. Select them all and create a report for everything so that you can see the information that you have. You'll see a lot of variables that are StreamStat variables, tau this, delta that you'll recognize from the equations. But take a look at them so you understand that you have those data. More importantly, what you'll see are the Q flows for design storms. When you generate a report, you do basin characteristics and flow characteristics and generate a report. You can print this as a PDF and save it. Down at the bottom of the report, it says you can export it as a HTML, print it, or print it. And I recommend printing it as a PDF so you have the report. That's what you're going to do when you turn things in for class. That's what you're going to use for your for project reports. Again, notice that this is an Esri product. This is what we were doing with our early watershed delineation model that we couldn't make work very well in our own labs, but works very well here. Now you understand the process that they go through to make these maps. They basically, for every square meter in the US, they've already built the digital elevation models. It's an incredibly robust process. We have drainage area. We have BFI, proportion of mean flow that is from groundwater. That's pretty important. 36% of this flow is from groundwater. That's good to know. Percent superficial geological or Ordovician and Mississippian rocks. That tells you how much. So 73%. Wow. This is it has rock outcroppings because of the mountains to the south. So that's the basin characteristics. General flow parameters. Again, we start to see those. Take a look. Get familiar with these. I'm not going to hold your hand through this. You guys are big engineers. Get used to learning how to do this work without, just be curious. Dig in. So use the exploration tool on the class watershed, Upper Town Branch, in order to explore. So you can measure things. You can do elevation profiles of your streams. Remember, as we start thinking about flow through our streams, we're going to have stream channel profiles. We're going to have measurements. This is the way you get those. So we have the tools now to measure. If I ask you, how long is the stream channel through our site, you can measure it directly. And you can also measure each of the sort of stream reaches directly. So you have the tools to do this. I want you to select all the scenarios and build a report for this basin, because you're going to use it time and again for the rest of this exercise. If we look at Upper Town Branch peak flows, we have the 2, 5, 10, 25, 50, 100, and 500 year return periods. And we have the Q values in cubic feet per second. We can change these to, or you can convert them yourself. We also have the upper and lower and upper confidence intervals, 95 and 5% confidence intervals. And you know how to calculate those with the standard errors. So we have the appropriate statistics now that you can build a probability distribution function for each of these values, return values. So we have reading documents for you. These are supporting documents. I expect you to be curious. I know time is short, always is. But this is what we do in the evenings while we're stuck inside anyway. Take a look. Get to know this. This is how you become an expert, by knowing the details. Glossing over doesn't make you an expert. Knowing the details does. Understanding the limits of the tool makes you an expert. The difference in a carpenter and a handyman is a carpenter knows what tools to use and has the tools in their belt. A handyman drives a nail with a wrench. Let's take a look now at StreamStat directly. As we go through StreamStats, the web link, the manual overview of the StreamStats, we'll take a look at those. StreamStat is intuitive to use if you've worked through any sort of a web GIS application. If you haven't, play with it, get used to it. You can Google StreamStats, you come to this site. So here's the application site. It's a web application. You can link this and download it, get a global map. First thing to do is identify where you are. You can identify any number of regions. You zoom in, it's intuitive there. Just zoom with your with any number of tools. I'm using the scroll wheel on my mouse. Arkansas, again, beautifully rendered. The base maps can be national maps. You can add streets. We can do world topographic maps. We can do gray maps for publications, dark gray maps for whatever purpose that would be. Imagery, which is usually composite Landsat imagery. Shaded relief maps, which I think are the most cool because I like the topography. So go back to the National Geographic map, which is funny that they just punted on their description and just said, that's what National Geographic looks like. So here's the key stream gauges. Continuous are blue, low flow or peak are yellow and red, and orange, low flow and peak. Partial, stage only. So we have this set of keys. We're not zoomed in far enough to actually tell. In fact, right now we have to have regional curves based upon which state we're working in, and it's asking us to select a state. Well, don't select that yet till you zoom in. It'll reduce most of those options for you. Down here at the bottom right is what you need to do. This is, I think, unfortunately placed, but it tells you here's what's necessary. Click this, do that. So this should be kind of up middle, but be used to kind of looking down here at the bottom right for instructions. Let's zoom into Northwest Arkansas. You can start to see we get a higher resolution with more maps, and we've reduced our options to Missouri, Oklahoma, and Arkansas. We zoom in even further, and it still gives us Missouri because we're connected. Now we can see Fayetteville. We can see Puddin Hill, but we can't see our streams yet. So let's zoom in even further. Now you see the resolution of the streets. Now we can see our site. Now we need user input to continue. First of all, let's tell this. All right, now we can say, now that we can see our site, now I want to zoom in even closer so we can start to see. And if you go to here and go to shaded relief, you really get a sense of the topography. Guess what? It didn't work at that scale. It's all gray. Go back to National Geographic. But to zoom out, you can see the topography really well. So now we tell it, okay, this is Arkansas. Now what it did is, because we told it's Arkansas, it put the Arkansas streams in. Notice how pixelated these are? Because they're pixels. They really are, it's a line that's got pixels overlaying them. And you notice that the pixels don't follow necessarily everywhere the streams are in these upper streams. It sort of shortcuts them. This is the best estimate we have for the streams. So just be aware of that. And sometimes you have to go in and modify this if it's critically important. So remember where our site is. If we zoom back, remember our site. Let's see, where is our site? So we have Highway 1671 over here. Oh yeah, here's our site right here. So south of Walker Park. So this is the 19th Street. This area is largely undeveloped, and the university owns this. Let's say the university wants to put a research center here and convert this into a research center, and we're trying to figure out what the flood zone possibilities are here. So this is our site. So we're going to delineate. So we're going to hit delineate, and now we get an X. So we click on that. We have to click on a stream. I'm going to click on the stream just before it converges with this other river because I don't want to hit the other river accidentally. And it says it's valid. That's good. Now we can delineate. And I click the bottom right button to delineate. And it's going to town. Go get a cup of coffee. This won't take as long as ArcGIS does over our less than effective network on campus, but there you go. Now you can edit the basin. You can start over, clear it. Cool thing is you can download it into GIS maps or into Google Earth or into other systems. In this case, we're not going to do any of those, but we can continue. So now we said, all right, that's our basin. Now it's building the statistics, querying regression regions within your basin. So it's doing all the statistical analyses I just showed you, and now we have them. Now, a scenario or one or more basin characteristics from the drop-down above must be selected to continue, because you can't just go do nothing. You got to tell it to do something. So we want general flow statistics and peak flows. You know, you can do all of these. You can do everything. And probability statistics. Let's do those. We don't, low flow, not so interested in because we're not doing water quality. Seasonal flow, we're not so interested in necessarily because we're interested in peak flow, not monthly either. And then we're also interested in basin characteristics. And so I want all the basin characteristics, percentage of basin covered by alluvial deposits. Well, not really, but okay. Adjusted slopes, 10 to 85% slopes in feet per mile, change in elevations. We're going to select everything because we're greedy for data. Select. It'd be nice if there was select all option. There's not. Doesn't take that long. Go through. I select everything. Soil index I really like. Tau average base flow recession time constant from March through April. See, these are for building those. So there, we got all that. Now we continue. Now it's calculating everything. After this, we get to generate a report. So notice that we have a weird shaped watershed. It's kind of a two major stream watershed. And what that means is we probably ought to be treating this as sort of as a Y-shaped watershed. But for this case, we're not going to do that. Now we can build a report. There we go. Continue. And there's our report. We can add titles, we can add comments. This is editable, and then we can download it or save it. So here we have all the basin characteristics we were describing. It's an incredibly robust report. By the way, if things are out of range, it tells you. This is the suggested range. This is a little bit small for the suggested range. We can print to PDF. We can download. We can download as a CSV, as a shapefile. As a GeoJSON. So the number of ways to download this, but print the report and you can download the shape files. It's incredibly robust. Remember, we have, more importantly, our statistical data here. So this process, this regression process, gives us Q values, maximum flows for given rainfalls. We know what these rainfalls are because we have the NOAA Atlas 14 to tell us what our peak rainfalls are for those maps for our regions. So we know what those are for each return period. And for those rainfalls, we then can tell what sort of Q values we're going to get. This is important because from here we can build a unit hydrograph that we can then extrapolate to any rainfall event to build a runoff hydrograph based upon any rainfall event in this basin. I hope you enjoy this. This is an incredibly powerful tool. Several years ago, I couldn't have used this tool because it wasn't available. So I want you to be effective users of this tool as good engineers. We will pick up with unit hydrographs in our next lecture.